Hello! In this video, we're going to be talking about rotational work. My name is Grant, and I will be your tour guide on this spiritual physics experience. So, first thing I want to talk about, as always, it's a good idea if you can turn your rotational problems and sort of think of them and think of their analogy in a projectile sense. So when we're looking at projectile versus rotation, in projectile, of course, we have distance, we have velocity, we have acceleration, we have the scalar quantity mass, and this can also be written as d, a distance covered. In rotation, we have quantities that are similar to these. For instance, replacing distance would be the quantity theta. Replacing the quantity of velocity would be omega. Now, be careful, this is not a W. It's also not a but. It is the lowercase Greek letter omega, which is the last letter of the Greek alphabet, of course. Now, the analogy to acceleration would be alpha. And then finally, the analogy to mass is I, or the moment of inertia. So let's recall, going back to work, let's recall our simple formula for work that we have in a projectile sense. So work is defined as force times the distance traveled. So let's say we have a point. We are going to call that point C. And let's say we have something, let's call it a point mass M, uppercase M, rotating around it in a counterclockwise direction. Now the radius of this circle is going to be R, our calculations, and the mass is going to be uppercase M. So let's say that the point mass travels in a counterclockwise rotation to this point. So it started here, this was its initial position, this was its final position. And the angle between those two is theta. So if we want to find the work using this formula, we take the force that was applied and multiply it by the distance traveled. Now, what is the distance traveled in this scenario? Well, would it be the straight line between these points? No, that's not the case. In this case, we are following the path of the circle. So what we need to do is find this arc length between the initial position and the final position. And a formula you can use to find that, the arc length is denoted S. And the formula is S is equal to theta R. Now it's very important to remember in this formula that theta must be in radians. Or else this formula won't work. And the reason why it must be in radians is because radians are the amount, the distance of a radius around the circle. So anyways, the way that I was taught this formula, my math teacher, Mrs. Shranowski, taught this to me. And she said that Mrs. Shranowski is going to be sore with you if you don't remember this formula. See, it kind of looks like S-O-R, sore, sore. It's a pun! All right, stick with me here. So, what we can do is go back to this formula here. Let's do a switcheroo. And we have W is equal to force times the distance here we said was going to be the arc length, S. And then using the SOAR formula, Grant will be sore with you if you don't remember this formula. We are going to replace the S with theta R. All right, so now we can make yet another simplification. So remembering back to a previous lecture, we recall that torque is equal to force times the radius. So if we have a circle here, a point in the center, a point mass out here, we are going to apply a force to it. We're going to call it F. And we have the radius R. The torque is the dot product of the force applied times the radius. I mentioned the dot product there. The dot product drops out if the force applied is at a right angle to the radius, which you're going to find in many problems. So, back to this. What do we notice here? Well, we notice a force, and we notice a radius. So, going back to this formula up here, we can replace both of those terms with torque. So work is equal to the torque times theta. Now, remember, this is rotational. Awesome. So this actually takes me back to this little chart we had up here. So there's actually one more analogy that we can draw between the two. In projectile motion, we have a force, and in rotation, we have torque. So they behave very similarly. Let's do an example. Let's just look at some formulas that might look very similar between projectile motion and rotation. So first, let's look at one you might have already gone over. Let's just look at the definition of acceleration. So the definition of acceleration is equal to a change in velocity over time. So what this means is velocity final minus velocity initial over time. So acceleration is the change in speed. Your speed or velocity is changing. Now let's look at this in a rotational sense. Alpha, your rotational acceleration, is equal to delta omega over time. So it is equal to your omega final minus your omega initial over time. Now what you'll notice is these two formulas are really similar. In fact, you literally just need to, every time you see a V, you replace it with an omega. Look at that, our little chart over here. So now let's look at another formula. Let's look at, in fact, let's look at this formula. Work in a projectile sense is equal to force times distance. So using our little chart, if we want rotational work, we look at our chart. Force is similar to torque, and distance is similar to theta. And look at that. We found exactly what we have here. There's a lot of other cases that you can do this in too. For instance, energy, which is a topic we'll go into next. So you don't need to know this now, but we're going to talk about it next lecture. The kinetic energy in a projectile sense is equal to class All right, I think I waited as long as Dora the Explorer for you to answer. And I know that none of you actually answered it. You were just waiting for me in that awkward silence. It's equal to 1/2 times the mass times the velocity squared. Now, I'm sure you can probably see where I'm going with this because of the excellent lighting in this here. That was a joke. When we talk about kinetic energy in the rotational sense, it is equal to 1/2. We're going to look at our chart and find mass is similar to moment of inertia, so I, times the velocity, we can relate that to omega squared. Now you might ask yourself, oh my gosh, how do I get that I? I'm sure you've already gone over that, but let's just go over it one more time. So let's say you have a point mass on a string rotating in a counterclockwise fashion around point C. This is our radius. This is our mass. So if we want to find the moment of inertia, the way we're going to solve that is I is equal to the mass times the radius squared. So look at this formula we have over here. Let's say we have this same scenario. We want to calculate the kinetic energy. So what we can do is replace that I term with this term here, mr squared. So that mr squared came from the I, right here, times omega squared. So this holds true if you have a point mass or a ring. They function the same because all of your mass is on the outside, rotating around a single point. All right. Well, that's all we have time for tonight. I just want to say sayonara. I don't know if I'll be here tomorrow.